Uh, okay, let's see if this thing is working. I should say I've pretty much never done anything like that before, so yeah, there's gonna be for sure some kind of troubles somewhere. But so this says offline. Oh no, determining quality. Okay, so uh, is this online or what? Yeah, so it says live, so it should be live. All right, okay, so it should be working. All right, so I mean the idea for this kind of work stream and stuff is well, there are like kind of a few reasons. So first one is I've been talking about the stuff I've been working on for a while on here on Discord, working mostly on the FFI bindings for BDK right now. And yeah, there were a few people that were kind of interested in that, so I thought it was gonna be cool to just show the way I do stuff, the kind of thought process. Also try to get some feedback, maybe from some people if anybody joins the live thing. Um, Also, I think it's gonna be pretty interesting as a kind of a documentation thing because especially for this thing that I'm working on right now, the documentation sucks. There's basically no documentation at all. So this is uh, potentially going to be useful, maybe even just for myself, just to go back and look back at previous videos and see what I was thinking and then maybe help. I mean, this is not going to be a substitute for documentation that's going to be in there as well. But I don't know, like kind of an extra addition to that, I guess. So yeah, let me check again. Everything is working, so audio should be fine. Yeah, I don't know. I think I can start. So maybe a little bit of a general introduction first, since this is like the first videos. It's the first video of probably a series of videos. I'm working on a project called BDK, which stands for Bitcoin Dev Kit, Bitcoin Development Kit, and it's basically a Rust library that you can use to build Bitcoin wallets or more generally anything that needs to touch Bitcoin in some sort of way. And this is written on in Rust because I personally really like Rust. I also think it's a very good language, very well suited for this kind of stuff. So yeah, the core library, which is BDK, and some of the other tools are in Rust as well. But the idea is that we also want to be able to let people use BDK from other languages, and this is where FFI bindings come into play. So one thing, we already did some like experiments with this BDK JNI thing, but this was like a very kind of an hack in a way. So the way this thing works is we have a little piece of Rust code that interacts with the JNI, the Java Virtual Machine JVM, and basically what we do is we convert on the Java side. Like if I want to make a function call to BDK, from the Java side we create a JSON string basically. So this is this part is purely in Java, actually in Kotlin, I think. But yeah, it doesn't really matter, I think. So yeah, we basically make a JSON string of the request we want to make. So you can like get a new address, and we're gonna create a JSON object with the wallet name and things like that. Then we send this over to the Rust code that kind of interacts with the JNI. So this piece of Rust code can, for instance, access strings in the JNI, I don't know, like JVM environment or whatever. And these are like the requests we support. We deserialize the JSON and match which request we got and send a response back as a JSON. So this is pretty cool, and it's very useful if you want to just prototype something quickly, but I don't know, it just feels kind of hacky to me. Also, it's not super efficient to keep converting stuff to and from JSON. So this was mostly an experiment. The idea now is to do them, to do the bindings properly. And since we want to make bindings for multiple languages, we are kind of trying to make basically just one single thing that can support all the languages we are interested into, which are mainly one is C, so basically being able to call BDK functions from C, and then Python for desktop environments, and then Java and Swift for the mobile side of it. So those are the main languages we're interested into. I think I haven't looked into it yet, but I think Swift is basically C. So I think you can, like, if you have a C header, you can use that from Swift or something like that. So not really looking into that too much right now. Also not really looking into the GNI stuff too much right now, because it's just easier to prototype everything on a desktop computer. So I'm mostly focusing on C and Python right now, but I'm trying to make something that is flexible enough that I can add more languages later on. And this thing is actually not in the Bitcoin Dev Kit organization yet, so it's in my own personal profile, and it's still called LFFI because this was like an hello word that I exposed. So yeah, it kept the hello name, but now it's not really an hello word that much anymore. It's already starting to map real BDK stuff. So I think I don't know what's best, if I should open it in my editor here, or let me first go back to master. We can try it this way. We'll see what happens. So basically the idea here is to, I don't think these colors are gonna show up too well in the video. Maybe see if I can change it very quickly. I don't know. Yeah. Okay, maybe this one. Okay, so basically the idea is that we have our BDK library, which is right here. And we want to keep this library like as a pure Rust library. We don't want to add anything to this. Also, we don't want to compromise the interface in any way. We want to make it like the best library possible that we can that you can use from Rust. So we use pretty extensively things like generics and all the nice things that Rust has. We take basically generics and we use the iterator traits and whatever. So this library is I think pretty cool to use from Rust. It's a pure Rust library, so it feels very nice. But yeah, it's kind of painful to expose directly those kind of stuff to other languages because you can't really express like Rust generics very well in other languages. Even if they support technically generics, it's still like a completely different model. So the first kind of concept idea that we have is that we're going to make a new crate that basically just wraps and exposes stuff from BDK, and it's this crate right here. So it's this bdk-ffi crate. So this crate, the main goal for this crate is just to re-expose stuff from BDK and actually also from Rust Bitcoin, because obviously a lot of the functions we have in BDK are going to take Rust Bitcoin types, like, I don't know, like the constructor for wallet takes a network, and this is defined in Rust Bitcoin. So we're also going to have to expose some stuff from Rust Bitcoin. And we are also going to maybe like change the API a little bit. So the idea is that we are not going to use generics and things like that so extensively. in this crate specifically because yeah, it's meant to be exposed to other languages. So is it still? Yeah, everything's still working. Nice. So yeah, this is kind of the idea for this crate. So we have things like we have a few modules, mainly the Bitcoin mod and BDK mod, where we expose Bitcoin stuff and BDK stuff respectively. And it looks kind of like this. So we declare a new structure called script that basically wraps the Rust Bitcoin version of script, and then we mark like this. We add some attributes to the structure that actually expose this structure to the other languages. So we're going to look into that in a second. But yeah, mainly the goal, like the job that this crate has, is just to declare stuff and wrap stuff from Rust Bitcoin or BDK and expose them. And we have like constructors and destructors. These are used. It depends on some languages, not all of them, but like in C, you have to explicitly destroy stuff. So use a destructor, which basically just takes the value, it moves the value into the function and then drops it. And yeah, we have like other kind of utility function, like create an empty script and things like that. So this is going to be probably a bit verbose in a way, because it's like most of the time we're just calling the same method on the inner like type. But yeah, we can also think about maybe making macros or things like that to automate this kind of stuff later on. We also use this macro ready. This is not to expose methods or anything. This is just to implement a few useful traits on the structure. So like for instance, here we use deref on self. Self is like our script type, but we implement deref with the original, like let's say, yeah, the original type as a target. So when I do self deref, I'm actually getting a reference to a Bitcoin script, not my own script, and then I can call a method on that one. And I think I can show you. This is not working. So it's probably in common, I guess. Yeah. So this is what this macro does. We implement from the original type to our type, and this assumes that our structure only has one field, which is called inner, which is of that type, and most of our structure actually follow this pattern, so this is fine. We implement deref, we implement deref mode, and we implement this into inner method, which returns the inner type, so that moves the inner type out of the structure and returns it. And we also have this trait, which we are not really using right now, but the main idea for this trait is that this is not exposed to the outside, so it can't be implemented from the outside. So basically, we automatically implement this trait for all of our structures. So maybe we can. The idea is that we know that all of our structures are going to implement this trait, which is kind of a marker in a way. So if we in the future need to do something like implement something for all of our structure, we can just implement it for every T that implements sealed. So it's not really used right now. It's kind of potentially a future thing. I don't know. We're going to have to see if we actually need it or not. We can also remove it in the future. So yeah, this is mainly what this crate does. Just wrap stuff and expose them. So it's interesting that we can't really expose everything. Like for instance, enum, they can be exposed to C but not to Python, because we use one thing that's called PyO3 to generate a lot of the Python, like the kind of glue code between Python and the Rust code and BDK, and they don't support enums, even though like they exist in the Python language, but they don't support exposing them. So we always have to expose only structures, even for enums. Like network is actually an enum in the Bitcoin library, but we wrap it inside a structure. So yeah, it's just another fun fact. And yeah, the API then is not so great because we can't compare by value. Like if I have two structures, I can compare their value because most of the time I only have a pointer. I don't know what's actually inside. I only have a pointer to a structure. So we need like methods like oh, we actually don't have them here. It's in a separate branch. Yeah, we're gonna go to that branch later on. But yeah, we need methods like is Bitcoin, is testnet, or things like that to know what's the type, what's the like variant of the enum, because we can't compare directly from the outside. So this is not really optimal, but I don't think we can do anything better right now. So yeah, we just have to do those workarounds. So yeah, I think somebody joined on Discord or something. I have no idea what this was. Yeah, so yeah, this is basically it. We just declare stuff. Also, we declare modules like a Bitcoin module, and we declare structure inside and we expose them. Most of the like magic is actually inside a separate crate, which is called derive, because it contains procedural macros. And in Rust, you are basically forced to have a separate crate if you wanna export procedural macros. So this is the derive crate, which is this one. Basically, the idea for derive is in derive we define those procedural macros like expose mod, expose struct, expose imp, and things like that. And inside this crate we do all the magic, like we, for instance, if we expose a function, for instance, so when we expose an entire imp block, we are basically exposing individual functions. What we do is we look for the types of the type of every argument, and we see if the type is, let's say, compatible with the language we are targeting. For instance, if we are targeting C, we can take a Rust string as an argument because the Rust string is a type that only exists in the Rust world. We have to take basically a character pointer and then perform the conversion. So then create a Rust string from a raw character pointer. So these procedural macros, what they do is they replace, for instance, the types. They also sometimes change the name of the function, and they do quite a lot of stuff. And basically the end result is a function that can be, like in this example, a function or a structure or whatever, that can be used from the other language without having to manually like writing code specifically targeting that language. So here I can just write string, and this is going to work. When I target C, this is going to be replaced with the right type, and everything is going to be done like transparently. But this is going to work in C. And also if I then target Python, when we target Python, a lot of this kind of magic is actually done by Pyo3. So in this case specifically of Python, we don't have to map the string type to anything else because Pyo3 understands the string type from Rust and knows how to map that to a Python string. So yeah, so in Python we're not going to do as much work, but we also need to do a few things there. So we're going to get to that later on. So yeah, also one thing I guess I should mention is that the idea is that this library can only be compiled for one individual language at a time, which I think is I think it makes sense. I don't see why one would like to build a library that works on C and on Python at the same time. I mean, it could be useful for some very weird cases, but yeah, most of the time is like it's kind of an edge case. So the idea is that we only support one language at a time. So you can target either C or Python or whatever. We do that through features from Rust. So we have a C feature and a Python feature, and you always have to enable either one or the other, not both of them, and not none of them. Otherwise, it's not going to work. And as we add more languages, we're just gonna add more features. And we also have some dependencies that are optional, and they're enabled only when a specific feature is enabled. Like for instance, PyO3 is only enabled when we want Python, and then cbind that we use to generate the C header, or libc, those are all included when you use C. And we also pass the feature, the language we want to derive. So derive also has the same kind of concept, where we have one feature for every language, and this is how we know which language we are targeting, basically. So derive works in this way. We have basically a trait, which should be in derive. I think it's lungs. We basically have this trait, which is called lang, that can be implemented for every language that we want to expose. So right now it's all implemented for C and Python. As I said, this can be implemented for more languages later on. And basically the idea is that the rest of the derive of the code of this derive trait is gonna like parse the code and interpret what's going on. And I don't know, do we have a function, do we have a module, a structure, whatever, and then it's gonna call this individual function for this specific language to, I don't know, like expose a function or expose a module, expose a structure. And what you receive is a mutable reference to an item. And these are all types that come from scene. I don't know how it's pronounced, but I think it stands for like syntax. And basically this crate has all the utilities you need to parse Rust code. So our proc-macro only gets a token stream. So it just gets a bunch of tokens, and we use scene to parse them into actually like usable objects. So for instance, this item fn we see here, this is defined like that. So we have all the attributes that the function has, the visibility, the signature of the function, a block that contains our code. So those functions, they receive a mutable reference to usually some kind of item, and they can do whatever they want with that item and return a result. We also return the ident. Ident is an identifier, so it's basically a name for something in the code. It can be like the name of a function, the name of a module, the name of a structure, something like that. We usually return it because if we change the name, we need to know that the name changed, because we might need to do some extra processing later on. So for instance, in Python, when we expose a function, we also have to add that function to a module, because you don't have like, I don't think bare function exists in Python. You always have functions as part of other modules. And the idea is that if we change the name, we need to know that we changed the name, because then we need to add the new name to the module. So this is why, yeah, we return the identifier. Some other languages like C, they don't really need to do that. They kind of ignore that. But yeah, this is why. And we also have a way to expose traits. This is actually the most like complicated part, so we're probably going to do that another time. We have functions to convert the input types and output types. Input and output stands for a type that is crossing the boundary in a way from the perspective of our Rust code. So basically, an input here is actually it's the other way around, I think. So like function arguments are inputs. So this is from the perspective of Rust. So the idea is that this type is coming from a different language and it's coming to us. So it's like an input to Rust. So this is kind of the concept. So for instance, function arguments are converted using this method here, because if I have a Rust function that is being called from another language, we are getting some data from the other language into Rust as a kind of an input into Rust. and vice versa, the return type is converted using the output because it's something that we return and we output to the other language. And there's actually one thing that I find really confusing, which is when you have to deal with callbacks. So like I can take a function or whatever, it depends on the language how it's called, but like in Python I think it's called lambda. In C it's like a function pointer. But basically when I wanna get from the external language something that I can call, and it's kind of confusing because everything flips in that case. So basically the function arguments, they become outputs because now I'm from Rust calling like a C function or a Python function. So the arguments I'm giving this function, they're going from Rust to something else. So they're actually output. So I don't know, just kind of a fun thing. I found that really confusing when I was working on it. And then we have like some kind of utilities like these provided methods. The only one we have is convert fn args. Fn args is, well, fn arg is a function argument. So it has, there are basically two variants. So receiver is when you have like some variant of self. So this is the full function argument with name and the type. And this is just self in some kind of way, like reference or mutable reference or whatever. So the idea is that we have a bunch of fn arg. So for instance, in item fn, actually in signature probably, in signature we have, we have a list. So this is basically a list separated by a comma of fn arg. So we want to convert all of them into the new arguments for the new type. And what this method does is we expand them as arguments, and we're going to look at that in a second. And we just create a new vector with all the individual arguments. So we start from an empty list of arguments and an empty token stream, and this is used for conversion of arguments. So the idea is that for every argument we get potentially more than one new args when we map them. And one example for this is, for instance, like when I want to get, let's say I have a function that takes a vector of, I don't know, integer as an argument. And in Rust, it's a single argument. It's like a vec of, I don't know, I32. But if I'm getting this from C, for instance, I'm getting a pointer to some piece of memory. And usually I also need something else, which is how many items are there in the vector. So this is like one example of one argument that gets expanded to more than one new argument. So this is why we use extend and everything, because args is potentially more than one. And comb is actually just a bunch of tokens. The idea is that those handle the conversion. So in this case specifically, where we have a pointer to some piece of memory and the length for how many items are there in the vector, this conversion is going to contain the piece of code that takes those two and creates a real Rust vector. Most of the time we try to do that without allocating new stuff. So if we can be efficient, we try to do that, but it's not super easy. So a lot of time we actually have to clone and whatnot, which is not ideal. But yeah, basically this token stream is gonna accumulate the conversion for all the types, and then we return it. So yeah, basically this is the kind of idea. So if you want to implement a new language, you implement this trait, you add the new feature, and everything should work in theory. We also have some other like utility kind of traits. We have this to convert to snake case, which is used in a few places. And we have an enum for errors in general that we want to return. We also have, usually languages also have their own specific error type, which is this one. but we also want to be able to wrap a lang error, which is like the base error, into that other type. So for instance, I have a C error that has these C specific variants, but also it can be created from a lang error to basically wrap those errors if they happen somewhere. Yeah, so now one example of an implementation of this is the C one. So it derives C lang ESRS. So this is like one language that we want to expose. What we do is we define a structure which is just like an empty structure. It doesn't really matter. It's just kind of something that we can implement the traits on. So like we implement lang for C, and we want to expose a function. And what we do is, a lot of stuff. So for instance, is we look for potentially extra like attributes. Like in this case specifically, if we have a destructor, we're going to do something with the types. So I'm not going to go into all the details right now. But yeah, this is like one example of we look for we iterate over all the arguments of the function, and for every argument, first of all, we don't expect any kind of self in that, so we return an error if that happens. And for everything else, we replace the type with destroy of type. So this is another, this is a structure that is specifically designed basically to wrap stuff that we want to destroy. But yeah, so basically the concept, without really understanding what this thing does, the concept is, this is one example of we need to change the inputs of a function in a specific way for the C language, and we do that. And for Python, it's actually different. In Python, we don't even need a structure because everything is handled by PyO3. So for instance, in Python, what we do is we completely ignore functions that are marked as destructors. And then we convert all the arguments and convert the return type. And then we replace the entire item fn, so the entire function, with a new one, which has no mangling. So this is like, we don't want the compiler to, actually, I don't know exactly how to describe that, but basically when you have like, if I have a structure inside some of let's say a couple of modules, the compiler is going to generate a name that represents the path that you can use to reach the structure. So in the final library, or in this case, it's actually a function, but in the final library, you don't get like a symbol for the specific function that has the name of the function. You also get a much longer name, which is called mangled name, that contains more information about the path that leads to that, like the modules that contain that function. And we don't want that because in C, we want to be able to like call functions and then link with functions that has a very simple name, no like modules and stuff. So this basically tells the compiler to emit a function that has that specific name that we have here. No more weird stuff about the path and things like that. And pub extern C, I'm not really sure what this does to I don't know if this is like kind of an int for the compiler or something. But yeah, basically the idea is that we then use cbindgen, which is a tool designed to generate C headers for a Rust project, basically. And this tool goes through your code and looks for functions that are that are marked with no mangle and that have pub extern C fn. So we need that to make sure that the cbindgen tool picks up the function. I'm not sure really what this changes in the actual code, but even if it doesn't do anything, we still need to add that, for cbindgen. Then we have we import a few traits and types that we use basically to perform conversion from one type to the other. and then this is like expanded to all the conversion for every individual argument, and it's a linear. So the new function becomes a function that performs the conversion. Then we take the original code for the function and we put it in here. And when we call this, since this is a closure, this is going to see all the variables that are present here. So the conversion declares a variable with the same name that the original argument had. So this block then sees those and can use them and can do basically everything it needs to do. And then we also perform a conversion for the output finally. This right here means that, for instance, if we have a type that we want to return by reference instead of as a return type, this right here is going to make sure that we take our underscore output and write that into the correct argument instead of returning it and things like that. So yeah, this is one example of a function conversion. I can show you also the Python version, which is probably a bit easier to understand because a lot of the conversion stuff is handled by Pyo3. So this is for the pen. So this is the Python version. One thing we have in Python that we didn't have in C is we expect to be in a module at least. So this argument right here is the list of basically nested modules that contain our function in this case. So we have, let's say if we have like module A and B, and then we have function C, when we try to expose function C, mod path is going to contain A and B. And since we can't expose functions like bare functions in Python, we expect to have at least one item. Otherwise, we're going to return an error. And this is one example of language-specific error. So we don't have this error in C because in C we can expose. There's no concept for like modules in C, so we can expose everything. But here we do have that. So yeah, we need to make sure that we are in a module. Otherwise, we're going to expose a function, but it's not going to show up in the final Python executable. And then again, we do this. This is like kind of standard. Looks like what we're doing in C: convert every argument, convert the return type, and then we create this, which is again kind of similar, but this time we mark that with Py function, which means that the Pyo3 Py function procedural macro is then going to pick up this and do all its stuff. Again, we have the argument, the return type, input conversion, output conversion. So it is kind of similar in a way. It's just different attributes and whatnot that we use. So I think I could also show you how this is expanded later on. So we don't need that. So I use cargo expand to do that. So it's a tool that you can install through Cargo. I think it's called cargo-expand. So it's like it's install. Oh, don't need. Okay, cargo install cargo-expand. Yeah, and this is pretty useful because you can see basically the code, what the code looks like after the procedural macro has done its stuff. And I'm also gonna comment out these two models because otherwise we're gonna have huge amount of code and we're not gonna be able to see anything. I'm just gonna like let's say define a new test module very quickly. So it should be expose mod and we can try to expose like a function, let's say, that takes function, and we can take like a number and return the double of that number. So we can do cargo expand features C, I'm also gonna add variables just to see what's going on. Why no such command? Isn't this? I think I've installed this already, but let's see what's wrong. Okay, no, it was not installed, I guess. So yeah, we're gonna have to wait a second here, I think. Oh, I think I've heard some Discord stuff. Oh yeah, somebody joined us. Yeah, no, it went away. All right, let me check this stream again. This is all working fine. Oh, looks like we have one viewer, which is nice. My first viewer. Yeah. So yeah, I was basically saying with cargo expand we can see what the code looks like after the procedural macro is done is stuff. So instead of seeing, like if we didn't have, we can try commenting them out just to test. See if this works now. Yeah. Double dash V. Okay. Oh, this didn't work. Why is that? Failed to run testing command. This is okay. I think this is probably our build.rs, which is doing something weird. You can try commenting it out just to see if that's the problem. Like here, you can do this. Expect. Oh yeah, right. Should comment this out as well. Oh, okay. We need to use the nightly compiler. Yeah, I forgot about that because when you do cargo expand, it basically runs Rust-C with some options that are still I don't know, that it can be used only on the nightly compiler. So yeah, we're gonna need to do that, and I think I also need to install it here. Yeah, so it's gonna have to install this here. So yeah, this is basically like a clean VM I made, so I still have to finish up installing all this kind of stuff. I'm also gonna share the configuration. I'm using NixOS in this VM, so in theory, if you wanna try, I mean, you don't really need anything special in your environment, but if you wanna like really reproduce this environment, you can take my configuration file for NixOS, and you should be able to recreate basically the same environment. But again, we don't really need anything special, so I don't think that's super useful. But yeah, so we have nightly here. Let's try again. Okay, it's working now. So I think I can also uncomment this. So this is now running with the procedural macros commented. So this should basically expand to the same code once this is done. Yeah, builder-s for some reason takes a long time, like the first time it runs. So the builder-s, it doesn't do anything in Python, and in C it runs C bindgen. So it generates the bindings header file. For some reason, yeah, it takes like a really, really long time the first time it runs. Even if, like in this case, we're not really exposing anything. We don't really have, everything is commented out. So I have no idea why that's the case, but yeah, this is it. So yeah, there's a lot of other code. This is code coming from other modules, but the main thing we are interested into should be somewhere around here, I think. Oh yeah, it's down here. So our mod, yeah, you can see that it's basically the same thing that we wrote here. So we have a module and we have a function, and that's it. If we uncomment those now, well, I can also show you that the bindings are empty because cbindgen ran but it didn't find any function that had the right, like pub extern C and whatnot. So the binding file it created is basically empty. Now we can uncomment those, so we are going to expose the module, which doesn't really do anything in C, but we still need to do it like for consistency with the other languages, and then expose the function itself. Yeah. And this is what we get now, which is already starting to look a bit more complicated. And also we should, let's see, yeah, and we have the function here. So this is the signature of our function, which makes sense. It's the name matches, and we take a unsigned 32-bit number, and we also return 1. And this is what it gets expanded to. So the argument is renamed. We basically add like a prefix because since one argument can expand to more than one, we use this like kind of as a counter. So like if val was expanded to more than one argument, we would have val0, val1, and whatever. Then we create like a tuple with all the arguments that make up one like original argument. So in this case, it's again only one. But if we add more than one, we have a tuple with more than one type. And then, yeah, we just assign it to a variable with the original name. So our closure that runs here expects to find something that is called val, and it's going to find it because it's here. So this is all part of the input conversion. In this case, it's not really doing anything, but we kind of follow this pattern because in other cases, we need to actually perform conversion. So it's useful to follow this pattern because usually we would have here, this would not be like let val equal temp val. It would be let val equal something that performs the conversion on temp val. And the same goes for the output. Since, I mean, those are just integer numbers, so it's not really, we don't need to do any conversion or anything. So same for the output, we run our closure. And then the output is, again, just the output. We don't really do anything crazy. But yeah, this is kind of like the concept, for instance. And if we actually try to expose that to Python, it's going to look much more complex because Pio3 adds. Oh, we don't have Python installed in here. Yeah, we don't. So I think it's called Python 3. Let me check again. Python 3, yeah. So we can install that real quick. And it's 3. Yeah, let's just do this. Rebuild. Actually, I've never tried running this under NixOS, so hopefully it's not gonna break or anything. Yeah, because I think it's gonna look for some at least kind of headers from Python because it needs to link, like compile and link with some Python stuff. But I don't know. Let's just see what happens. So now we do have interpreter. Okay, try this again. Oh, no, actually it works. So so here you can see Pio3 doing a lot of its magic. So our function becomes this, which is again very similar to what it was before, just without the pub extern C and whatnot. But then since we call the Pio3 procedural macro on this is all the other like code that is generated, which we don't really care about. We just take it. It's done by Pio3. We just use it this way. So yeah, this is just a bit of an example of how a function is exposed. I think I could show you the way we do type conversions with these map from and the map to traits that you could see here that we imported here. So we have, this is actually code that is part of the of our main crate, like of the bdk-ffi crate, because this is not part of the derived crate. So the derived crate create some code that uses those traits. So like the derive crate emits this piece of code, but this then ends up in the bdk-ffi crate. So those traits need to be in the bdk-ffi trait, or potentially an external third crate. But now for convenience, they are still in the same one. So those are in, let me see, mapping. Yeah. So src mapping. So we basically have those two traits. The reason why we have new traits, we're not using from and into from Rust, is mainly that we want to be able to implement, like to do this, like implement something for every t, or for every t that basically for any type. And we get a lot of conflicts if we do this with from and into from Rust, because from is an external trait from the perspective of this crate. So you can't like implement an external trait on every type. You cannot implement it for your own types, not for other external types, because if you have an external library, that library could implement the trait as well, and we will have a conflict. But in this case, we define the trait ourselves, so we can basically implement it on whatever we want. So this gives us a little bit more of flexibility. And yeah, so this is mainly the reason. So we define a map from trait and a map to trait. Map from takes s from a source and returns self, and map to does the other way around. And we also implement, like, make this default implementation where you can convert something to itself, which is useful in a few. It's a useful like generalization in a way. So we can do like something, and even if we're not really converting the type, we can still use map from and map to. Yeah, and it's not gonna break. And then we have language specific mapping. So for instance, for C, we implement from a character pointer for a string, and this is what we do in the conversion. This is the way we do arrays basically. So we implement from a tuple of a pointer to a type f, and the usize, which represent the length. We make a conversion from this tuple to a vector of t, where t can be mapped from f. So we basically have a pointer to an array of f, and we know how to convert from f to t. So we can create t from f, and we also have the length. So we can create a vector of t by basically creating a vector of f, which is what we do here. So we create. We also need to use quite a bit of unsafe functions here, obviously, because if you are taking like a pointer from outside of Rust, the Rust compiler can't really check that that pointer is valid or anything. So we need to use unsafe for that. But basically, we trust that in this case, the C code that is calling this, I don't know, like a Rust function with those arguments is not lying about the length and everything. So we create basically a slice from this pointer with this len, and this is a slice of type f, and then we map every individual item to t. So yeah, this is one way of doing arrays. There's actually another way which is more convenient in a few cases, because it doesn't map to multiple arguments. So this is like if we had a Rust function that takes a vector of something, it would be expanded to two arguments, one for the pointer and one for the length. And this is kind of inconvenient in many cases. So we also have this other thing where we have this R structure, which is just a structure that contains the pointer and the length. So instead of taking two arguments, we only take one that contains the two things we need. And then we do basically the same thing. Now we could also, I guess, refactor that to something like that if we wanted to reuse code. But yeah, I mean, it doesn't really matter all that much right now, I think. But yeah, we can probably do something like self map from. Yeah, so we can like reuse this piece of code because this is just another way of encoding the same thing. So here it's in a tuple, and here it's just one type that contains both of them. Yeah, we implement also the other way around. Like this is, we can take a string and transform it into a C character pointer, for instance. We also have to forget the string ourselves, otherwise when this function ends, this value would get dropped, and then we would be returning a pointer to freed memory. So we need to forget about it, and then it's the responsibility of the basically the caller on the C code that receives this pointer is its responsibility to free that pointer. We also do the other way around for vectors and options, but yeah, I think you get the point by now. We have this rate to perform conversions, and we define how to do the conversion in here. And then I think we can maybe start looking a little bit into how those traits are used. So for instance, in the C language, we define how to convert input. Convert input, this one. And this is our function that defines how to convert every input type. So the default is to not touch it. So in the end, we have unchanged same type. But if our type matches one of those special cases, basically, we do something specific with it. So one example is when way to. Okay, so yeah, like one example is if our type matches a string, so it's we have those utility functions to match like the specific type or a generic type, where we can match anything that is a vector, and we get back what's inside our vector. But in this case, we're matching like the specific type. So if we match something that is a string, we say that we're gonna map it from a vector, because again we can take more than one argument, but in this case it's only one. A vector of a const character pointer. If you get a vector, this is a bit more complicated, but basically we look into the inner type, and we convert the input first, because I don't know, let's say we have like a vector of strings, we're gonna have to change that into an R in this case of character pointers, because the string itself, again, we can't really take that. So we also need to perform the conversion on the input, and then in this case we do this, which is kind of a simplification, but it works for now. It's basically, since we could get more than one source type, so this conversion could tell us that if you want to create, like, let's say a string, you need two arguments, two different types. So this is why source is it's a plural, but here we can't really use more than one type inside our generic. So we use this as tuple, which is just, if you have more than one type, just create a tuple out of those, so that in the end it's still just one type. So yeah, it's basically, it's not ideal, and this is basically the reason why we prefer doing vectors, basically why we prefer mapping vectors to R, to those. It's because we can still, we map basically one-to-one, so then we can do nested vectors, because yeah, the n type is going to be like R of something, because otherwise if we were doing the other way, which is mapping from vector to two arguments, which is a pointer and the length. If we had like nested vectors, we would add a vector. We need like a pointer to a tuple because the inner type is a tuple of our type and of a pointer to our type and the length. And we can't really do that, especially like from C. We can't create a pointer to a tuple to a Rust tuple. We don't know how to do that. So we would not be able to expose nested vectors basically, and we need those for a few things. So yeah, this is why we changed it up to, instead of being two types, to just one type, which is this R that contains the two members. It's just much easier to handle. It will work fine for a simple vector, but then if you start doing nested vectors, for instance, you have those kind of issues. This is again another kind of special case. So I don't know if you remember the thing we were doing on the destructor. So we were replacing the type with destroy T. Destroy is not really like a type that exists. It's just kind of a marker that we can then detect here, and we change it from T to mut pointer of T. And we also define basically how to do to take this pointer as part of the conversion. We define how to take this pointer and take ownership of it so that we destroy it when our like function finishes. So this is just a way to basically like mark the type before, and then when we get down here, we realize that this is something that we need to destroy. So we're still going to take it as a pointer, and then we're going to do the conversion to take ownership of it and destroy it. This is how we map function pointers. So basically how we map callbacks. This is like very complicated, so I'm not going to get into this right now. But yeah, just wanted to show like one example. So the way you would do, like, let's say I need to take a new type as an argument, and it's not a type that is like a native type, like, I don't know, an integer that is the same both in C and in Rust. I need to take in like a complex type. What I would do is I would come in here in the convert input, I would add a special case for that type, and then I would define the mapping right here, basically. So let's see if this still compiles now that I changed that. Yeah, so I think it, oh, maybe, I don't know, because cargo expand doesn't really compile it. Yeah, no, it's actually not working. Yeah, I don't know. Oh yeah, because it's R of F. Oh yeah, this is bigger. Yeah, okay, so it works. Yeah, I don't know, just a little refactoring there. Let's see what else I could show you. Yeah, so the way we do expose structure, it's one of the, I think, easiest to understand because we don't really do anything. It's not like code or anything. There's no actions being done in a structure. So usually what we do is well, define a structure, call it my struct with value. Again, U32 because it's easier, because it's not a type that needs conversion or anything. If we do that and we expand it, it's going to look the same. The only thing we do is we add rep C, which basically tells the compiler to represent it in memory like the C way, which means that then we can C binding is going to recognize this and realize that this function, basically C can safely look into these structures, can safely look into the members of the structure, knows the offset and everything, and so it's going to expose it into the bindings file, which I don't think we have anymore. Yeah. I think I'm going to need to run cargo check because the build rs doesn't run. or maybe it's not exposing it. Yeah, I think it's not exposing it because we're not really using it anywhere. So it realizes that we're not really using it. So maybe we can maybe you can return it here. And let's see if this works. Oh yeah, can leave private type. Should be public. Okay, so let's see if it's all right. So this worked. So now our function, instead of returning u32, now returns my struct, and we have like the definition of our struct here. This is because again our procedural macro added repress C on the structure, so it's basically like compatible with C. The problem is sometimes you have things inside your structure that are not compatible with C themselves. So in this case, we only have a u32 inside, and that's fine because again, it's the same thing in both languages. But if we start having like a string, for instance, in here, let's say, yeah, the value is the string version of the value. So it is string, I think. This already, I think it should give a compile error or some kind of. Yeah, so this is like a warning. Basically, the problem here is that we have a string which is not FFI safe because it's not a type that can be understood from C, for instance. So the solution to that is to make basically opaque structures. And the solution here is, I think we're already actually adding that. So yeah, I think the compiler is getting confused because we're already adding this repress C, but it's still telling you consider adding that. I think what it should say is that you should consider adding that to string because it's the string inside our type that is not FFI safe. It's not our type itself. Like our type becomes not safe because of the string. So yeah, basically the short answer is we can't really do that. So we need to make basically an opaque structure, which is like a structure where we only get the, I think it's called forward declaration in C. So we basically know that it exists, but we don't know the internal layout, or at least like the C compiler doesn't know the internal layout of that. And we do this by using opaque here. So it's like an argument that you can give to expose structure. And when you use opaque, it's not going to add that repress C. So now the structure itself is fine, but we still have the problem that we are trying to return it here. But we can't really do that because it's not a type that the compiler, the C compiler knows. So the C compiler only knows that it exists, but it doesn't know the layout. And we can't return it by value because the C compiler would need to know, I think, how much space this thing takes on the stack in order to be able to return it by value. So, for instance, what we want to do in this case is return it by reference, which basically means this function. Well, maybe I can first show you how this is declared here. Yeah, so basically this gets declared like that. So it's like, yeah, this thing exists. But if we use this header in a C program, it will fail to compile because the compiler would say, I don't know what's the layout of this structure. I don't know how can I take this as a return value of a function because I don't know how much space it takes. So we need to change the way we use the structure. We will never use the structure like the structure as a value. We will always only use pointers to the structure because pointers have a fixed size, so the compiler knows what size they have. And the idea is that for the C code, those are just like opaque pointers. The C code doesn't know what's in them. It just says this pointer that can give to other Rust functions to stuff on them. So one example of how we would do that, we would change the mapping in our C file, and we would say if we match that type, return it by reference. And there are already, I think, a few types that need to do this. Oh yeah, this is actually in the convert output, obviously, because this is not an input, it's an output. And yeah, it's basically like those are other types that we need to return by reference because those are opaque types. So we just add if our output is my struct, return it by reference, and it's gonna be a mutable pointer to my struct. So now if we do cargo expand again, yeah, you can see that a few things change. So in this case, since we said that we wanted to return this by reference, and this is what we defined here is the reference type, but we need to take a pointer of that type, basically like a double pointer, and we're going to write into that the pointer of the structure, like on the heap. So basically what happened here is that since we want to return that by reference, we add the new argument of that type. Basically, we just added the one more mutable pointer. And then you can see the input conversion is still the same because we're not touching the value or anything. But now the output conversion is doing a bit more work. So what we do is once we have our output, we put that into a box, and we use box into row to get a row pointer to those data that are now on the heap, and then we set the pointer value to that value, and we don't return anything. So the return type is changed to nothing basically, and we add a new argument that takes that value. So now the C header should, yeah, so now the C header reflects that. So now it's a void function and it takes a double pointer of this type. Now this thing works because in C I can basically define it like I can define a pointer variable, so like my struct PTR, let's call it struct PTR, and then I can call my function with a value, and then I can say no. Maybe we can initialize it to null, but whatever. So this is how I can call this function now, and at the end of the function, I'm gonna have my struction pointer. It's not gonna be null anymore. It's gonna have some value inside, and again, the C side doesn't know what's going on. It just has this pointer that you can pass to a new function and then do more stuff. So yeah, this is how structures are exposed. I think I'm gonna stop here for this video because this is already like a lot of information, I guess, to process. But yeah, so basically the main idea for this video was just to give kind of an introduction on what's going on with this, and I think, I don't know, more or less at least the concept that, you know, we have a new crate where we expose stuff. We have a crate that defines procedural macros, and those procedural macros operate on functions and structures and modules that we want to expose, and then basically they change them a little bit in order to make them, let's say, compatible with the language they are targeting. Maybe just gonna show you quickly how this thing looks in Python instead, because it's quite a bit different actually. So when we expose a structure in Python, we basically create a Python class. So I'm going to show you the exposed version first. And again, there's a lot of code that we don't generate. So this code is all generated by Pyo3. What we generate is, it's basically, we emit the same structure, but we tag that structure with a specific like procedural macros from Pio3 that says expose this as a class. So expose structure. Yeah, what we do is basically we add this attribute, either that or subclass, if we give like we can give opaque, which is ignored by the Python version, by the way, but like opaque, which is an option that we can give to expose struct, we can give the subclass option, and that's going to be used to make a class that can be extended, basically. But yeah, so basically the only thing we do is we don't really change the structure or anything. We just add the PyClass attribute, and then Pio3 generates all of this code for our structure. And I think I can virtualenv. Probably not. Maybe Python 3 and no module name virtualenv. No. Okay, so let me install virtualenv very quickly. It's not in here. Maybe it's this one. Yeah, just gonna Google it because I'm still very new to NixOS. NixOS Python virtualenv. Oh yeah, you can create the Nix shell. You can create like a fake virtualenv. I don't really want to do that. I just want to do like a standard virtualenv. Okay, so it's Python 3. Okay, so I think this is why we had that thing. Right, so I think this is part of this thing. Okay. Okay, so I don't know, let's see. Where do I have to add this though? Because I'm not sure. Like, do I just define that in my configuration something? I don't know. Okay, I think we're gonna go with this way because it's quicker, and I think I know how to do that. Yeah, I can just do Nix shell. So let's do something like this. I think it's called shell.nix. Shell.nix. Paste all that. And I need like, is it here or here that it goes? It is not. Probably not what I need. Let's try with this way. Actually, no, I don't need anything specific because I think this is gonna already create a separate like package directory or whatever. It works. I don't know. It works. I don't know. Let's try it this way. Doesn't really matter. So I can go into my Python here, and there's a README that very briefly says how to use all of this. So we're going to need to install basically some setup tools for Rust stuff. Okay, so it's not in here. So do we have to add that to the shell as well? Let's Google that again. Yeah, the reason why I'm using NixOS is mainly to be able to create an environment that I can reproduce easily. So the idea was, if somebody wants to follow those steps at home, can just, copy my my configuration and just recreate the same environment. But yeah, as you can see, I'm not super familiar. Oh, then I can probably do that. I think uh, Python 3.8. Yeah, so I have to, maybe I need to do this to get the full version first, I guess. And then I can use that. Okay, so we need, so it's this one, I guess. I don't know, let's try. No. Maybe NixOS. No, I don't. Oh no, it's, this is Nix shell -p, I think. What's set? Okay, I have no idea. Okay, so let's just, I think NixEnv installs that in your system. I didn't really want to install it. I just wanted a shell with that package. But yeah, I don't know. I just need a quick thing as long as it works. Let's try this way. Yeah, so, okay, so I think this worked. I'm not sure if what happens if I use again the shell here. I don't know if I'm gonna have teeth inside it. I do. I don't know. Let's see if that works. So yeah, I'm basically just gonna install those setup tools. Yeah, don't care about that. And then I think it's Python setup py develop. So this is gonna compile. Okay, so okay, yeah. So it's still trying to use that as its package directory, but maybe I can change it in some way. I don't know if you can install as a user. Yeah, I don't know. Not working. Okay, so let's check this. Python setup tools. So user. I know there's like a pip install user or something, which basically like installs in a, yeah, so this thing. Oh, this is that dash user. That's easy. No, it's not working. Warning size packages. I have no idea what all of this means. Let's try to go back to virtualenv because I think this is kind of what you need to fix those kind of problems. Python virtualenv. I think this is kind of what we need. Okay, so we can just do this in here then, I guess. Okay, let's try. So I'm gonna remove this. Fish. So it's like, okay, let's try. I think we're using Python 3.8, so with the capital. Okay, Python 3.8 full. Python 3.8 dash. No, packages dot virtualenv. I still don't think this is the right solution because in theory it should be able to figure it out like automatically that I'm using like Python 3.8 and not 3.7 or something. But I don't know. Just want this to work. oh yeah, maybe in the full there's more stuff. I guess maybe there's like pip included or something. I don't know. Yeah, virtualenv. Yeah, we do. Okay, this is looking good, I think. Okay, let's try it again. Okay, and let's not here. Python setup develop. Okay, I think it's working. Yeah, so it's basically compiling all the stuff, and it's gonna create a module. I think we're gonna have to change maybe a little bit the part where we expose that. So I think it's, yeah, because we expect to have a BDK module that we don't really have. So we're gonna have to comment that out because our module now is called test mod. But so if we launch Python, the main module is still called BDK, but now we don't have the BDK submodule anymore because we commented it out from here. So I think I can do like from bdk.test mod import everything. No, we have BDK. Yeah, so that's in BDK. Oh yeah, right. I have to change. There's another file that you need to change in setup.py, I think. Yeah, this is all just because I changed name for stuff. Yeah. Test mod. Yeah, try this again. But yeah, obviously you don't need to do that. Like when you actually use the real library, it's just, why is it not in here? So Rust extension, bdk test mod. Did it actually do anything? Because this was way too quick, I think. I don't know. There's nothing in here. Maybe this. See anything? Also, it shows the test mod. So wait, can I from bdk import test mod? Oh, okay, so it works. I don't know why it was not showing up, but yeah. So now we do have our test mod, and we have my struct, and we have the test function. I think it can maybe show. This is like a class, basically. And again, it's like completely opaque. We don't really have access to what's inside. We only have access to the like the definition of a structure, and we have our function, and we can like call our function with a value. I think it was, yeah, it was an integer, and it should return, yeah, it returns an object, which is again like an opaque object, but it creates an instance of our structure and returns. Yeah, so like a completely different compared to like the C version, which returns it by reference. But yeah, this is like all language specific stuff. So in the case of C, we map that return type to be returned by reference, and we don't do that in Python. So it's again like returned as a normal return type. I think I'm gonna check once more. Okay, so I didn't miss anything from the chat. And where is Discord? It's here. Okay. Okay, I didn't miss anything important, I guess. Yeah, so I think this is gonna be it for this video. I think I'm gonna I'm also gonna publish that to YouTube. Not super sure how to do that. I think there's like an option in Twitch to make it upload automatically or whatever, but I don't know, somehow hopefully it's gonna end up on YouTube, so I'm gonna try to make like a playlist with all those videos, and I don't know. Yeah, if you're interested in following this kind of stuff, you can join our Discord. We'll add like an invite link to the description, so you can join, and I will publish there um, when I'm planning to do those streams, and then you can, I don't know, join the voice chat if you wanna ask any questions, um, or even just use the chat if you prefer to do it this way. Yeah, so I think this is gonna be it. See you next time.